A star dies, and the entire universe shifts. This single event holds secrets about the fate of everything, from the planets we walk on to the fabric of reality itself. By the end of this journey, you will understand how the death of suns reveals the ultimate destiny of the cosmos. We will explore what happens when a star breathes its last, and how that violent, beautiful end seeds the universe with the very elements that make life possible. What mysteries lie hidden in the final moments of a star's life? And what do they tell us about our own place in this vast, evolving story? How does it feel to know that the end of something so distant and immense is deeply connected to your own existence? That immense journey begins not with a bang, but with a whisper in the cold, silent darkness of a nebula. These cosmic nurseries are vast clouds of gas and dust, the scattered remains of ancient stars that met their end long ago. For eons, these particles drift, but then a subtle shift occurs. A ripple of gravity, perhaps from a distant supernova's shockwave, stirs the cloud. Slowly, almost imperceptibly, pockets of gas and dust begin to collapse inward, pulled together by their own mutual attraction. As this core grows denser, its gravitational pull strengthens, drawing in more and more material. The pressure and heat at the center become unimaginable, climbing to millions of degrees until it crosses a critical threshold. In a flash, nuclear fusion ignites, and a new star is born, flooding its nursery with light for the first time. This newborn star then settles into the longest and most stable chapter of its life, what astronomers call the main sequence. Here, a star achieves a perfect, delicate balance. The immense force of gravity is constantly trying to crush the star inward, but this is countered by the tremendous outward pressure from the radiation generated by fusion in its core. In this core, atoms of hydrogen are relentlessly smashed together to form helium, a process that releases the energy that makes stars shine. Our own sun has been in this main sequence phase for about 4.5 billion years, and it has another 5 billion or so to go. It is the ultimate cosmic equilibrium, a stalemate between collapse and explosion that defines a star's prime. But this balance cannot last forever because the fuel is finite. How long this stable phase endures and what happens when it finally ends is dictated by one single factor from the very beginning: a star's mass. A star's mass is its destiny. Smaller, red dwarf stars are incredibly frugal with their hydrogen fuel. They burn it so slowly and efficiently that their lives are measured in trillions of years, far longer than the current age of the universe itself. They are the ultimate marathon runners. In contrast, massive stars are the cosmic sprinters. They live spectacularly bright but brief lives. Their enormous gravity creates ferocious pressure in their cores, forcing them to burn through their hydrogen fuel at a prodigious rate. A star 10 times more massive than our Sun might shine with 10,000 times its brilliance, but it will exhaust its fuel in just 20 million years, a mere blink in cosmic time. This entire process, from a nebula's quiet collapse to the final, desperate consumption of fuel, is known as stellar evolution. It is not a random series of events, but a predictable, step-by-step journey where each stage sets the table for the next. The type of death a star will experience, and the legacy it will leave behind, is written in its DNA from the moment it first flickers to life. The main sequence is merely the calm before the storm, a long, stable period that is really just a prelude to the inevitable and dramatic final act. Every star is born with a clock already ticking, counting down to an ending that will, in its own way, begin something new. Deep within the star's core, this stable balance is powered by a continuous, staggering release of energy. The process is called nuclear fusion, the engine that drives every star in the sky. Think of it as the most powerful and reliable furnace imaginable, operating under conditions so extreme they defy earthly comparison. At temperatures of millions of degrees and under crushing pressures, Hydrogen atoms are moving so frantically that they overcome their natural aversion to one another. They collide with unimaginable force, and in that collision, something miraculous happens. They fuse. The nuclei of these hydrogen atoms merge together to form a new, heavier element, helium. But in that act of creation, a tiny bit of mass is lost. And according to Einstein's famous equation, that mass does not simply vanish. It is converted directly into a colossal amount of pure energy. This is the energy that has poured from our sun for billions of years, warming our planet and making life itself possible. It is the source of starlight. This energy radiating outward from the core creates a powerful pressure that pushes against the star's own immense gravity, which is constantly trying to pull everything inward. For most of a star's life, these two titanic forces are locked in a perfect, delicate standoff. The outward push of fusion energy exactly matches the inward pull of gravity. This equilibrium is what keeps a star like our Sun in a stable, spherical shape for eons. But this engine is also a consumer. It steadily burns through its hydrogen fuel, transforming it into helium ash. Over millions or billions of years, the core begins to change. The hydrogen fuel depletes, and the accumulating helium, which is heavier, sinks toward the center. This is the first quiet step toward the end. The fusion process does not stop with helium, however. In the most massive stars, the furnace becomes even more potent. As the core grows hotter and denser, it can begin to fuse helium atoms into even heavier elements like carbon and oxygen. Then, if the star is massive enough, it will fuse carbon into neon, neon into oxygen, and so on. Each successive fusion reaction requiring higher temperatures and lasting for a shorter period of time. It is a desperate, accelerating race against gravity, creating the very elements that will one day form planets, rocks, and living beings. This cosmic alchemy, happening in the heart of a star, is what seeds the universe with the building blocks of everything we know. But every fusion reaction is a step closer to the engine sputtering out, setting the stage for a final, catastrophic failure of that perfect balance. This stable balance is temporary, a truce that must eventually break. For a star like our Sun, the first sign of the end arrives when the hydrogen fuel in its core is finally exhausted. The relentless fusion engine at its heart begins to sputter. Without the outward pressure from hydrogen fusion, gravity gains the upper hand. The core, now mostly inert helium, starts to contract under its own immense weight. This collapse is not a gentle shrinking, but a violent compression that generates a tremendous surge of heat. The temperature in the core skyrockets, climbing to over 100 million degrees. This intense, new heat ignites a shell of hydrogen surrounding the core, which begins to fuse furiously. The energy from this shell fusion pushes outward with incredible force, causing the star's outer layers to swell to a monstrous size. The star has now entered its red giant phase. It becomes a behemoth, bloated and brilliant. A star that was once a stable source of light transforms into a raging, unstable titan. Our own sun will one day undergo this exact transformation. It will expand until its outer atmosphere reaches the orbit of Earth, utterly engulfing Mercury and Venus. Our planet will not be spared, its surface scorched to a cinder, its very atoms vaporized and pulled into the star's chaotic embrace. From the perspective of the dying star, this is a necessary and violent rebirth. Its outer layers cool as they expand, shifting its light from a familiar white-yellow to a deep, ominous red. Yet, despite this cooler surface, the star's total luminosity increases dramatically. It becomes hundreds of times brighter than it was in its prime, a dazzling but deadly farewell performance. This phase is a paradoxical mix of breathtaking beauty and absolute destruction. The star is both creating and erasing worlds. Within its swollen interior, the hellish temperatures in the core now allow for the next stage of fusion. where helium atoms are smashed together to form carbon. This process releases another wave of energy, temporarily stabilizing the core once more. But this stability is even more fleeting than the last. The red giant phase is the beginning of the end for mid-sized stars, a final glorious act that fundamentally alters its solar system. It is the prelude that sets the stage for the star's ultimate fate, determining whether its death will be a quiet whisper into the darkness or a thunderous announcement to the entire galaxy. This brilliant, bloated state cannot last. For a star like our Sun, the red giant phase culminates in a surprisingly gentle release. The star's grip on its outer layers weakens, and they begin to drift away, not in a single explosion, but in a series of powerful stellar winds. These winds carry the star's own atmosphere out into the void, creating a vast, expanding shell of incandescent gas. What remains is the star's naked core, now exposed to the cold vacuum of space. This core, no longer supported by fusion, is a white-hot ember of degenerate matter, a white dwarf. It is a star compressed into an object roughly the size of Earth, yet containing a mass close to that of our original Sun. A single teaspoon of this material would weigh tons here on Earth. This incredibly dense remnant has no energy source left. It is a dying cinder, destined to do nothing but radiate its immense heat away into the darkness for trillions of years, slowly fading from white to yellow to red, and finally to a cold black dwarf. But before it fades, it performs one last act of cosmic artistry. The ultraviolet radiation blazing from the exposed white dwarf illuminates the expanding shell of gas it just expelled, causing it to fluoresce in a spectacular display of color and structure. This is a planetary nebula, a name that is a complete misnomer from early astronomers who thought their round shapes resembled planets. In reality, they are some of the most beautiful and complex objects in the universe, like the Helix Nebula, which appears as a giant eye staring back at us across the light years. These nebulae are not just beautiful, they are essential. They are the delivery mechanism for the universe's future. Within that glowing gas are all the heavy elements forged in the star's core, and during its final violent phases, carbon, nitrogen, oxygen, and more. This enriched material is scattered back into the interstellar medium, the raw material for the next generation. Every planet, every rock, every living thing is made from atoms that were once inside a star. And for many of those elements, their journey began when a star like ours died a peaceful death and gifted its remains to the cosmos. This quiet end is a rebirth in disguise, a final contribution that ensures the cycle of star birth and death can continue. But for the most massive stars, death is not a gentle exhale. It is a scream. For the most massive stars, this final surrender is not gentle. It is an apocalypse. When a star many times heavier than our Sun reaches the end of its line, its death is the most violent event in the universe since the Big Bang itself. Its core, having fused elements all the way to iron, faces an insurmountable problem. Fusing iron does not release energy, it consumes it. In an instant, the star's mighty engine, which has burned for millions of years, suddenly stalls. The outward pressure from fusion vanishes completely, and gravity, patient and relentless, wins the war in a single moment. The core collapses at a quarter the speed of light. In less than a second, an object the size of Earth is crushed into a sphere just a dozen miles across. The density becomes so insane that protons and electrons are forced together, merging into neutrons. The core becomes a solid, unimaginably dense ball of nuclear material, a neutron star. The collapse halts so abruptly that it sends a cataclysmic shockwave rebounding outward through the star's infalling outer layers. This rebound, fueled by a flood of neutrinos from the newborn core, rips the entire star apart in a titanic explosion. This is a supernova. For a few glorious weeks, this single dying star can outshine the combined light of every other star in its entire galaxy. It is a brief, blinding beacon visible across the cosmos. The energy released in that instant is more than our Sun will generate in its entire 10 billion-year lifetime. But this is not just a spectacle of destruction, it is the universe's most vital forge. The incredible temperatures and pressures inside the blast are the only places hot enough to create elements heavier than iron. This is where the gold in your jewelry is born. This is where the uranium that powers reactors is forged. Every ounce of silver, every atom of iodine in your body was created in the heart of a supernova explosion that occurred billions of years ago. We have witnessed these events throughout human history. In the year 1054, Chinese astronomers recorded a guest star in the constellation of Taurus, so bright it was visible during the day for nearly a month. That was the supernova that created the Crab Nebula, a tangled web of expanding gas that still glows today, a ghostly remnant of that ancient cosmic detonation. These explosions are the great recyclers of the cosmos. They blast these newly forged heavy elements across light years of space, seeding vast clouds of gas and dust with the raw ingredients for rocky planets, for oceans, and for life itself. A supernova is both an end and a beginning, a funeral pyre that also serves as a cradle. But the story does not end with the supernova's fading light. Left behind in the chaotic wreckage is the star's collapsed core, a neutron star. This is one of the most bizarre objects in the universe. Imagine taking the entire mass of our Sun, an object 1.3 million times the size of Earth, and crushing it into a sphere no wider than a city. The density is beyond human comprehension. A single teaspoon of neutron star material would weigh billions of tons, a mass equivalent to a mountain range compressed into a sugar cube. This incredible density is the result of a complete atomic breakdown. During the core collapse, the immense gravity was so overpowering that it forced electrons and protons to merge, canceling each other out to form a solid ball of neutrons. It is matter stripped down to its most fundamental, compressed state. Some of these neutron stars reveal themselves in a truly spectacular way. If a neutron star is spinning rapidly and has a powerful magnetic field, it can become a pulsar. Think of a pulsar as a cosmic lighthouse. It emits intense beams of radiation from its magnetic poles, and if those poles are not aligned with its axis of rotation, the beams sweep through space like the spinning light of a lighthouse. From our distant viewpoint, we detect these beams as a rapid, incredibly precise pulse of energy every time one sweeps across the Earth. The timing of these pulses is astonishingly regular, some ticking with more accuracy than an atomic clock. The first pulsar discovered was so rhythmically perfect that astronomers briefly nicknamed it LGM for Little Green Men, wondering if they had stumbled upon an artificial signal from an alien civilization. These cosmic lighthouses are far more than just curiosities. They serve as unparalleled natural laboratories for testing the laws of physics under conditions we could never recreate on Earth. By meticulously tracking the pulses from a pair of orbiting pulsars, scientists were able to confirm a key prediction of Einstein's theory of general relativity: the existence of gravitational waves. These are ripples in the very fabric of spacetime, caused by the acceleration of massive objects. The precise clockwork of the pulsars allowed researchers to detect the tiny, rhythmic distortions in spacetime as the two dead stars spiraled toward each other. In this way, the corpses of stars become our guides, helping us probe the deepest questions about gravity, matter, and the fundamental structure of the universe. They are the ultimate testament to a star's enduring legacy, long after its brilliant light has faded from view. Yet, even a neutron star is not the final word in cosmic collapse. For the absolute most massive stars, the force of gravity is so overwhelming that it crushes the core beyond the density of a neutron star. There is no force in the universe that can stop it. The collapse continues, squeezing matter into a single point of infinite density known as a singularity. This is the birth of a black hole, A black hole is the ultimate expression of gravity's power, a region of space where the gravitational pull is so intense that nothing, not even light, can escape its grasp. The boundary that marks this point of no return is called the event horizon. Think of it like a waterfall on a river. The water flows smoothly until it reaches the edge. Once something goes over that edge, there is no coming back. The event horizon is that edge in space-time. Inside it, the laws of physics as we know them break down. Time and space swap roles, and all matter is drawn inexorably toward the central singularity. But a black hole's influence is felt far beyond this invisible boundary. Its immense gravity warps the very fabric of space-time around it, like a heavy ball resting on a stretched rubber sheet. This distortion can bend light from stars behind it, creating strange optical effects called gravitational lensing. When a black hole drifts through a cloud of interstellar gas or has a companion star, its pull draws matter inward. This material doesn't fall in straight down. It spirals into an incredibly hot, rapidly spinning disk called an accretion disk. Friction within this superheated disk causes it to glow with intense radiation, often outshining entire galaxies and making the black hole's presence known across vast cosmic distances. Some of this matter, rather than falling in, can be funneled and ejected at nearly the speed of light in powerful jets that extend for thousands of light years. These mysterious objects, once purely theoretical, are now known to be common. At the heart of our own Milky Way galaxy, and likely at the center of every large galaxy, sits a supermassive black hole, a gravitational monster weighing millions or even billions of times more than our Sun. They are the dark hearts around which galaxies spin. By studying these ultimate cosmic sinks, we are not just learning about destruction. We are probing the very limits of our understanding of reality, testing the laws of gravity, and uncovering clues about the final fate of matter in the universe. These stellar remnants, from white dwarfs to black holes, are not merely tombstones. They are active participants in a grand, never-ending cycle of cosmic recycling. When a supernova explodes or a planetary nebula expands, it does not simply vanish. It scours its surroundings with a shockwave of energy and a rich cloud of newly forged elements. This ejected material, containing everything from life-giving oxygen to precious gold, is blasted out into the interstellar medium. It mixes with the pristine hydrogen and helium from the Big Bang, enriching vast cosmic nurseries with the heavy elements required for complexity. This enriched cloud then becomes the raw material for the next generation. Gravity pulls these clouds together once more, and within them, new stars begin to form. But this time, they are not alone. Those specks of carbon, silicon, and iron coalesce into solid particles, then rocks, then planets orbiting the newborn sun. A star that died billions of years ago provided the very ingredients for the world you now stand on. This is the profound truth behind the phrase "we are stardust." It is not just a poetic idea, it is a literal scientific fact. Every single atom in your body, from the oxygen in your lungs to the iron in your blood to the calcium in your bones, was created in the heart of a long-dead star. That carbon was forged in the gentle death of a sun-like star. That iron was hammered into existence in the final second of a supernova's cataclysm. You are, in the most direct way possible, the universe experiencing itself. You are a collection of ancient stellar remnants, assembled into a form that can look back at the night sky and wonder about its own origins. This cycle of death and rebirth is the engine of the cosmos. It turns destruction into creation, ensuring that the end of one story is always the beginning of another. This fate is not reserved for distant, anonymous suns. Our own star, the steady presence that has warmed Earth for billions of years, is on the exact same clock. In roughly 5 billion years, the sun will exhaust the hydrogen fuel in its core. The delicate balance that has defined its long, stable life will shatter. Gravity will take control, compressing the core and igniting a furious shell of hydrogen fusion around it. The energy from this last-ditch effort will be so immense that it will force the Sun's outer layers to expand outward at a terrifying rate. Our Sun will swell into a red giant, its diameter stretching out beyond the orbit of Mars. Mercury and Venus will be swallowed whole, consumed by the star's advancing atmosphere. Earth will not be engulfed, but its fate is sealed. The planet will be scorched, its oceans boiled away, its crust melted into magma, orbiting as a dead, blackened cinder within the star's tenuous outer reaches. This transformation will be the most dramatic event in our solar system's history since its formation, a final, fiery rearrangement. After this blazing phase, the Sun will gently exhale its outer layers into space, creating a beautiful, ephemeral planetary nebula. For about 10,000 years, this glowing shell of gas will be illuminated by the intense ultraviolet light from the exposed core. That core, no longer supported by fusion, will remain as a white dwarf, an Earth-sized ember of carbon and oxygen. It will initially blaze with searing heat, but with no energy source left, it will slowly, over trillions of years, cool and fade from white to yellow, to red, and finally to a cold black dwarf, a dark diamond in the void. This timeline is so vast it defies human imagination. 5 billion years from now is a distance so great that all of human history is but a single, fleeting moment within it. Yet, knowing this ultimate end invites a profound reflection. Our existence is a brief, bright spark in the calm between stellar storms. It forces us to consider our legacy, not on geological timescales, but on cosmic ones. The story of our Sun is a single, predictable chapter in a universal playbook, a pattern repeated with variations across the galaxy. By reading its fate, we decipher the destiny of countless other stars, understanding that creation and destruction are two sides of the same coin, forever spinning in the grand cycle of the cosmos. This grand cycle of stellar death and rebirth is the unseen architect of every galaxy. The demise of stars does not happen in isolation. Its effects ripple outward, sculpting the vast structures we see in the night sky and governing the very pace of cosmic evolution. A galaxy is not a static collection of stars. It is a dynamic, breathing ecosystem, and the death of its suns provides the crucial feedback that maintains its balance. This process begins with the most violent of endings. When a supernova explodes, it does more than just create new elements. It unleashes a tremendous shockwave that travels through the surrounding interstellar gas. This wave can compress cold, quiet clouds of hydrogen, squeezing them just enough to trigger the gravitational collapse that births new stars. In this way, a star's death can be the direct cause of new stellar birth, a cosmic chain reaction where one generation literally gives rise to the next. We see this beautifully illustrated in the history of our own Milky Way. Our galaxy is not a single, homogeneous entity. It is composed of distinct populations of stars. The oldest stars, found in the galactic halo and bulge, are metal-poor, meaning they formed from the pristine hydrogen and helium left over from the Big Bang. Their deaths through early supernova seeded the surrounding gas with the first heavy elements. Later generations of stars, including our Sun, formed from this enriched material. They contain a richer mix of elements, a testament to the stellar generations that came before them. This sequential enrichment has gradually built up the complex chemistry we see today, directly influencing the types of planets that can form and, potentially, the life that can arise. Yet, the influence of stellar death is a double-edged sword. While a supernova's shockwave can trigger star formation, the incredible energy it releases can also have the opposite effect. The same blast can heat vast regions of gas to extremely high temperatures, making it too energetic and diffuse to collapse under its own gravity. It can even blow the gas completely out of a small galaxy, effectively shutting down its ability to form new stars altogether. This is the feedback loop that regulates a galaxy's growth. It is a self-regulating system where starbirth and stardeath are locked in a delicate dance. Too many stars forming at once leads to more supernova, which then heat and disperse the gas, slowing the rate of new star formation. This process prevents a galaxy from burning through all its fuel in a single, brief burst of activity, ensuring its longevity over billions of years. By studying these cycles, astronomers can read a galaxy's history like a book written in starlight. The mix of elements, the locations of different star populations, and the presence of hot, diffuse gas all tell the story of countless stellar lives and deaths. Understanding this grand interplay allows us to predict not only the future of our own Milky Way, but to comprehend the life cycle of every glittering island universe in the cosmos. The universe is 13.8 billion years old, a span so immense it challenges all human intuition. This vast timeline is not empty. It is the canvas upon which the epic of stellar evolution unfolds. The very first stars, known as Population 3 stars, ignited when the cosmos was just a few 100 million years old. They were behemoths, composed only of hydrogen and helium, the pristine elements forged in the Big Bang. Their lives were spectacularly short and violent. They burned with ferocious intensity and died in colossal supernova within a few million years. Their explosive deaths were the universe's first act of recycling, seeding the void with the first heavy elements. This first generation of stars fundamentally changed the cosmos, polluting the primordial gas with the ashes of their demise. It was only after these pioneers lived and died that the universe could form the second generation of stars, the metal-poor Population 2 stars, and eventually stars like our Sun, which are rich in metals and belong to Population 1. We are the beneficiaries of countless stellar generations that came before. Each generation built upon the last, enriching the cosmic environment with more complex elements. This entire process, from the first star to our Sun, required almost the entire history of the universe to unfold. We can actually look back and witness these early epochs. When we point our most powerful telescopes at the most distant galaxies, we are not just looking across space, we are peering back in time. The light from those ancient stars has been traveling for over 13 billion years to reach us. We see them not as they are today, but as they were when the universe was in its infancy, a cosmic fossil record written in starlight. By studying them, we learn about the conditions after the Big Bang, confirming that the early universe was indeed a simpler place, dominated by those first massive, short-lived stars. Their rapid life cycles acted as the universe's first clocks, marking the passage from a hot, featureless soup of particles to a structured, complex cosmos filled with the ingredients for planets and life. The death of stars does not just create new elements, it drives the universe forward through time, ushering in new epochs and setting the stage for everything that follows. This cosmic alchemy is known as nucleosynthesis, the process that forges the very atoms of our existence. While a star's core can create elements up to iron through steady fusion, building anything heavier presents a monumental challenge. Fusing atoms larger than iron does not release energy, it consumes it. A star cannot simply burn these elements as fuel, it requires a cataclysm. That cataclysm is a supernova. In the heart of that unimaginable explosion, in a maelstrom of energy called the Are process, or rapid neutron capture, neutrons are slammed into atomic nuclei at an incredible rate. The atomic nuclei grab these neutrons faster than they can radioactively decay, building heavier and heavier elements in a fraction of a second. This is how the silver in your photograph, the iodine in your body, and the platinum in a laboratory instrument are born. They are forged in the most violent conditions the universe can provide. But there is another, even more extraordinary cosmic crucible. When two neutron stars spiral inward and finally collide, they create a kilonova, an event so powerful it shakes the very fabric of space-time. This collision spews out a cloud of material rich with neutrons, triggering the Are process and creating staggering amounts of the heaviest elements. Scientists now believe a single neutron star merger can create and fling outward hundreds of times the mass of the Earth in solid gold and platinum. Look at a periodic table. Every single element beyond iron, from copper to uranium, owes its existence to the death throes of massive stars. These are not mere curiosities. They are the foundation of our material world. Without them, Earth would be a barren ball of rock and ice. The silicon in rocks, the oxygen in water, the phosphorus in our DNA, and the iron in our blood all originated in these stellar explosions. This scattered stardust is what allows for the complex chemistry of planets and ultimately, the chemistry of life itself. We are not just living in the universe, we are literally made from its most dramatic and beautiful endings. The death of a star is the ultimate upheaval for its planetary family, a reordering of cosmic real estate that leaves nothing untouched. For a star like our Sun, the red giant phase is a wave of absolute destruction. As the star expands, its outer atmosphere engulfs the inner planets. Mercury and Venus vanish instantly, consumed by the stellar furnace. Earth's fate is to be scorched, its atmosphere stripped away, its surface melted into a global ocean of magma, orbiting for a time as a barren rock within the star's tenuous outer layers. The habitable zone, that precious band where liquid water can exist, is pushed radically outward. Worlds once frozen solid at the system's edge, like the moons of Jupiter and Saturn, might suddenly find themselves bathed in a temporary, warming glow, their icy shells melting into subsurface oceans. But this new warmth is a fleeting and cruel gift, lasting only until the star sheds its outer layers and collapses into a white dwarf, leaving the entire system in a permanent, deep freeze. A supernova's impact is even more chaotic and far-reaching. The initial blast of light and radiation from a nearby supernova would be enough to sterilize any world within dozens of light years, scouring its surface of life. But the physical shockwave that follows hours or days later is what truly reshapes the system. This wave of energy can rip planets from their orbits, flinging them into the void as rogue planets drifting between the stars. It can shatter asteroid belts and tear apart the delicate disks of material that might have one day formed new worlds. The entire architecture of the planetary system is scrambled in an instant, a cosmic reset button pressed with unimaginable force. Yet from this chaos, new possibilities can emerge. The debris from a supernova, mixed with the shredded remains of planets, can coalesce into a new, second-generation disk of material around the stellar remnant. A pulsar, the super-dense spinning corpse of a star, was found to host the very first exoplanets ever discovered, worlds of pure diamond likely formed from the ashes of the cataclysm that created their parent star. Even a white dwarf can sport a new ring of rocky debris, the pulverized remains of asteroids and perhaps even planets that survived the initial red giant phase, only to be torn apart by the dwarf's intense gravity. Within these disks, the cycle of planet formation can begin again. This means a star's death does not always mean the absolute end for its system. It can be a transformation. While the inner worlds are gone, new planets could potentially form at much greater distances, born from the enriched material the star expelled in its death throes. The ingredients for these new worlds are now far richer, laced with the carbon, oxygen, and other heavy elements forged in the star's final moments. It is a sobering and majestic thought that a solar system's story might have multiple volumes, its fate inextricably linked to the life and death of its star. We witness these cosmic deaths from an incredible distance, not as spectators, but as detectives analyzing the evidence left behind. Astronomers piece together the story of a star's demise by carefully studying the light that travels for millions or even billions of years to reach our telescopes. The primary clue is the light curve, a simple graph that plots a star's brightness over time. A supernova, for instance, creates a very distinctive curve. Its brightness skyrockets to a sharp peak as the shockwave tears through the star's outer layers, then gradually fades over weeks or months as the expanding cloud of debris cools. This single measurement tells a profound story about the explosion's energy and the amount of material ejected. But light holds even more secrets when we break it apart. Using a technique called spectroscopy, astronomers pass starlight through a prism-like instrument to create a spectrum, a rainbow band etched with dark and bright lines. Each of these lines is a unique fingerprint, corresponding to a specific chemical element present in the stellar material. By reading these spectral lines, scientists can determine the exact composition of the gas ejected from a dying star, identifying the presence of oxygen, silicon, or even gold. This is how we know the heavy elements in our bodies were forged in these cataclysms. We are essentially doing cosmic forensics, analyzing the chemical residue of an explosion that happened long ago. Our ability to perform this analysis has been utterly transformed by powerful observatories placed above Earth's blurring atmosphere. The Hubble Space Telescope has provided decades of stunningly clear images, allowing us to watch the intricate expansion of supernova remnants like the Crab Nebula in exquisite detail. Its successor, the James Webb Space Telescope, operates primarily in the infrared, a type of light that pierces through cosmic dust clouds. This lets Webb peer into the very hearts of stellar nurseries and the dusty shrouds of dying stars, seeing processes that were once completely hidden from our view. This technological leap has unlocked a new era of discovery. In 2017, a monumental event was observed. Gravitational wave observatories detected ripples in spacetime from the collision of two neutron stars. Within moments, telescopes around the world and in space swiveled to that patch of sky, capturing the event in every wavelength of light. This coordinated effort confirmed a long-held theory that such violent mergers are indeed the cosmic crucibles where the heaviest elements, like gold and platinum, are created. We didn't just theorize about it anymore, we saw it happen. Each observation, from a single flicker of light to a complex spectrum, is a vital piece of the puzzle. They are the data points that transform the epic story of stellar death from a beautiful myth into a confirmed, and even more beautiful, scientific reality. These cosmic crime scenes demand theoretical frameworks of immense power to explain what we observe. The equations describing a white dwarf, for instance, rely on a bizarre quantum principle known as degenerate matter. When a star's core collapses into a white dwarf, it is squeezed to such an incredible density that electrons are stripped from their atoms and packed together. But these electrons, following the rules of quantum mechanics, refuse to be squeezed into the same state. This creates a powerful outward pressure that halts the collapse, a final stand against gravity that has nothing to do with the heat of fusion. This degenerate pressure is the only thing keeping a white dwarf from crushing itself further. But there is a limit. An Indian astrophysicist named Subramanian Chandrasekhar calculated this ultimate threshold. He found that if a white dwarf's mass exceeds about 1.4 times that of our Sun, even degenerate electron pressure will fail. Gravity wins absolutely, and the collapse continues into a neutron star or black hole. This Chandrasekhar limit is a fundamental boundary written into the laws of physics, a line that separates one cosmic fate from another. For the most extreme collapses, we must turn to Einstein's theory of general relativity. His equations describe gravity not as a force, but as a warping of spacetime itself. They predict that if enough mass is compressed into a small enough volume, it will warp spacetime so severely that it pinches off from the rest of the universe, forming a black hole. These are not just abstract ideas. They are precise mathematical predictions that have been confirmed again and again by observation. To test these theories, we use some of the most powerful computers on Earth to simulate stellar deaths. Modeling a supernova is one of the most complex challenges in all of science. You must account for nuclear physics, fluid dynamics, neutrino interactions, and general relativity all at once, in a chaotic three-dimensional environment. Supercomputers run for months to simulate just the first second of a core collapse. These simulations have revealed a possible solution to the supernova mechanism problem, showing how neutrinos streaming from the newborn core can deposit enough energy to reboot the shockwave and power the explosion. Similarly, simulations of dying sun-like stars show how complex magnetic fields and stellar winds can sculpt the beautiful, intricate shapes of planetary nebulae, explaining why we see delicate butterflies and hourglasses instead of simple, expanding bubbles. Yet for all our knowledge, profound mysteries remain. Astronomers have observed supernovae that seem to fail, where a massive star disappears without the expected brilliant fireworks. Did it collapse directly into a black hole, swallowing the evidence of its own death? And how exactly do dying stars launch those incredibly focused jets of matter, moving at nearly the speed of light, that we see in gamma-ray bursts? The precise physics that can accelerate material so efficiently is still an active frontier of research. These models do more than explain the past. They allow us to project future cosmic events. We can predict with confidence that the star Betelgeuse in Orion will end its life in a supernova explosion within the next 100,000 years, an event that will be visible from Earth even in broad daylight. Our theories paint a dynamic picture of a universe in constant flux, where the death of a single star is a complex event governed by physical laws we are still striving to fully understand. This human impulse to find meaning in the stars is ancient and universal. Long before telescopes or spectrographs, our ancestors looked up at a sudden, brilliant new star and wove it into their myths. The sudden appearance of a supernova was rarely seen as a simple natural event. It was an omen, a portent of change, a message from the gods. Chinese astronomers in 1054 meticulously recorded the guest star that created the Crab Nebula, interpreting it within their complex celestial bureaucracy. Half a world away, Native American artists may have captured the same event in petroglyphs, a brilliant star next with a crescent moon. These celestial events were woven into the very fabric of human culture, a reminder that the cosmos was alive and watching. This tradition continues today, though the language has changed. The death of a star is no longer seen as an omen for kings, but as a profound inspiration for artists, writers, and musicians. It represents the ultimate drama, a story of life, death, and rebirth on a scale that dwarfs our own. From the epic poetry of the stars to the haunting visuals of a planetary nebula in a science fiction film, these cosmic endings fuel our creativity, pushing us to express the inexpressible grandeur of the universe. This confrontation with cosmic scale inevitably leads to deeper philosophical questions. The astronomer Carl Sagan famously reflected that we are made of star stuff, a realization that is both humbling and empowering. It connects us intimately to the cosmos, yet it also highlights our breathtaking impermanence. A human life, even the entirety of human civilization, is a fleeting spark compared to the billion-year life of a star. Watching a star die forces us to confront our own mortality, not with fear, but with a sense of perspective. The philosopher Blaise Pascal wrote of being terrified by the eternal silence of these infinite spaces, and that feeling is understandable. We are tiny, fragile beings on a small rock, orbiting an average star in a remote corner of a common galaxy. Yet our ability to understand this story, to trace our origins back to the heart of a supernova, is what gives us a unique place in the cosmos. We are the universe's way of understanding itself. This knowledge invites a quiet reflection on legacy. If a dying star can seed future worlds with the ingredients for life, what is the legacy of a single human life within the brief moment we are given? Our time is short, but like a star, We have the capacity to create light and warmth that extends far beyond our own existence. The cyclical nature of stellar death offers a powerful metaphor for existence itself. In nature, we see cycles everywhere, from the changing of the seasons to the water that evaporates, forms clouds, and falls again as rain. The universe operates on this same principle, but on a grand, epic scale. The death of a star is not an end, it is a return. It is a necessary phase that enriches the cosmos, ensuring that future stars, planets, and life can arise. This cycle of creation from destruction is a fundamental rhythm of reality. It suggests that endings are not to be feared, but understood as a natural and essential part of a much larger story. We are all part of this endless cosmic dance, born from stardust and destined to return to it. Our atoms one day perhaps finding their way into new suns and new worlds. This is not a cold, mechanical process, but a beautiful, generative one. It tells us that we are not just in the universe, we are of the universe, participants in a grand, ongoing transformation that has been unfolding for nearly 14 billion years. Every star that dies is a single note in a much larger symphony. A symphony whose final movement will play out over timescales that dwarf even the life of a galaxy. The fate of all stars is inextricably linked to the ultimate destiny of the universe itself. A cosmic endgame dictated by a mysterious force we are only beginning to understand. For much of the 20th century, cosmologists debated between two grand possibilities. One was the Big Crunch, a dramatic finale where the expansion of the universe would eventually slow, halt, and reverse. In this scenario, all of creation would come crashing back together in a fiery inverse of the Big Bang, a cosmic collapse that might, in theory, recycle everything for another potential beginning. The other possibility was the heat death, a far more quiet and chilling end. Here, the universe would expand forever, its galaxies drifting ever further apart until the last stars burned out, leaving behind a cold, dark, and empty void where nothing ever happens again. For decades, the question hung in the balance, a theoretical tug of war between gravity's pull and the universe's initial outward momentum. The answer, it turns out, was hidden in the light of dying stars. In the late 1990s, astronomers made a shocking discovery by studying a specific kind of stellar death, the supernova of white dwarf stars that cross the Chandrasekhar limit. These explosions, known as Type 1, a supernova, are crucial because they all reach roughly the same peak brightness, making them perfect standard candles for measuring vast cosmic distances. By comparing how bright these supernovae appear to how much their light has stretched, or red-shifted, scientists can calculate how much the universe has expanded since the star exploded. The results were not just surprising, they were revolutionary. The data revealed that the expansion of the universe is not slowing down due to gravity, as everyone had expected. It is accelerating. Something is actively pushing galaxies apart, and that something has been named dark energy. This discovery turned cosmology on its head. The fate of the universe is no longer a simple question of gravity versus momentum. It is now a story dominated by this mysterious, repulsive force. If dark energy continues to behave as we observe it now, the heat death, or what is more precisely called the Big Freeze, becomes the most likely outcome. Picture a future, trillions upon trillions of years from now. The last stars will have long since died, their white dwarf and neutron star remnants having cooled to absolute zero. Black holes will slowly evaporate away over almost unimaginable eons through a process predicted by Stephen Hawking. The universe will become an unimaginably vast, ever-expanding emptiness, a thin, cold soup of isolated particles where the temperature approaches absolute zero and no energy flow is possible. It is the ultimate state of equilibrium, a permanent and silent stillness. The alternative, the Big Crunch, now seems far less likely given our current measurements, but it is not entirely ruled out. If the nature of dark energy were to change, if it weakened or became attractive, the expansion could still slow and reverse. The distant galaxies would begin to blue shift as they hurtle back toward us. The cosmic microwave background radiation would heat up, and eventually, everything would collapse into a singularity. Whether this would lead to a rebirth, a new Big Bang, is a matter of speculation, a beautiful but unproven idea. The light from dying stars has given us our most profound glimpse into the far future. Each supernova is a point in the greatest experiment imaginable, telling us not only how a star lived and died, but where the entire cosmos is headed. We are left with a humbling realization. The same stellar deaths that create the elements of life are also the beacons illuminating a cold, dark, and lonely end for the entire universe. Our cosmic story, which began in a blaze of light, appears destined to conclude in an endless, expanding whisper of darkness. The universe's most resilient life might not bask in the warmth of a young sun, but cling to existence in the cold cinders of a dead one. Could a planet orbiting a stellar corpse, like a white dwarf or a neutron star, ever be habitable? This is not just a question for science fiction. It is a frontier of modern astrobiology, pushing our understanding of life to its absolute limits. Consider a white dwarf, the Earth-sized ember of a sun-like star. It no longer generates energy through fusion, but it radiates a tremendous amount of residual heat, glowing white-hot for billions of years. A planet orbiting within the right distance of this fading glow could, in theory, have a surface temperature suitable for liquid water. This new habitable zone would be incredibly close to the white dwarf and profoundly stable. Since a white dwarf cools so slowly, this zone would remain fixed for eons, offering a potential haven for life for far longer than the main sequence lifetime of the original star. But the challenges are immense. Any planet that close would be tidally locked, with one side in permanent, scalding daylight and the other in frigid, endless night. The only region with temperate conditions might be a thin twilight band along the terminator line. Furthermore, the white dwarf's intense gravity would shred any large, passing asteroids or comets, creating a dusty debris disk that could periodically rain down onto the planet. Life would need to be incredibly hardy to survive in such a precarious environment. The scenario becomes even more extreme around a neutron star. These ultra-dense remnants emit fierce X-rays and particle radiation, bathing any nearby world in a constant, lethal shower. However, some theories suggest a protective atmosphere could shield a planet's surface. More intriguing is the potential for tidal heating. If a planet orbits a neutron star in a slightly elliptical path, the star's phenomenal gravity would constantly stretch and squeeze the world's interior, generating immense internal heat through friction. This process could maintain a subsurface ocean, like the one suspected to exist on Jupiter's moon Europa, completely independent of starlight. In such a place, life would not look up at a sun, but would be nurtured by the heat of a planet's own tortured flexing, a biosphere hidden beneath a thick shell of ice, illuminated only by the faint, rhythmic pulse of its dead star. Science fiction has long explored these ideas, from worlds orbiting pulsars to civilizations surviving their sun's red giant phase. But scientists are now seriously investigating these hypotheses, using telescopes to search for the chemical signatures of atmospheres around white dwarfs, a telltale sign of a surviving or newly formed planet. This search redefines the very meaning of habitability. It forces us to ask not just where life could begin, but where it could endure and for how long. If life can persist in the cold ashes of a dead solar system, then the number of potential homes in the galaxy might be far greater and far stranger than we ever dreamed. These cosmic detectives are armed with tools of astonishing sensitivity, listening for the faintest whispers of the universe. Gravitational wave observatories like LIGO have opened an entirely new sense, allowing us to feel the ripples in spacetime itself. When two neutron stars spiral together and collide in a cataclysmic kilonova, they don't just release light, they shake the very fabric of the cosmos. LIGO's immense L-shaped detectors, with arms 4 kilometers long, can measure distortions thousands of times smaller than an atomic nucleus, capturing the specific chirp of these ultimate cosmic collisions. This is not just observation, it is a new form of astronomy where we can hear the universe's most violent events. Our vision has been equally transformed. The James Webb Space Telescope peers into the infrared, a part of the light spectrum that cuts through the obscuring dust clouds surrounding stellar nurseries and the expanding shells of dying stars. It reveals the intricate chemistry within these clouds, showing us the very building blocks of new planetary systems being forged from the ashes of the old. This is just the beginning. The upcoming Vera C. Rubin Observatory, with its colossal 3.2 billion pixel camera, will scan the entire visible sky every few nights. It will not wait for us to point it at known objects. Instead, it will watch for change, automatically detecting the sudden flare of supernova as they happen, perhaps catching one in the very first moments of its explosion. This torrent of data will allow us to create a real-time movie of the dynamic universe, tracking the life and death of stars on an unprecedented scale. The pursuit of these cosmic questions does not happen in a vacuum. The technology developed to study the stars consistently spins off into innovations that benefit our daily lives. The exquisite sensors designed for space telescopes have been adapted for more precise medical imaging, allowing doctors to detect diseases earlier. The algorithms created to process the enormous datasets from sky surveys are now used to improve everything from weather forecasting to artificial intelligence. The very internet you are using to watch this was developed by physicists at CERN to share particle physics data. Each time we push the boundaries of our cosmic understanding, we are also building a better toolkit for understanding our own world. These technological leaps are not just giving us more data, they are giving us deeper insight. With every new observatory, with every more sensitive detector, we are adding new pages to the Chronicle of dying stars, translating their final messages with ever greater clarity and bringing the ultimate fate of the cosmos into sharper focus. This profound connection to the cosmos carries with it a quiet responsibility. As the first life forms we know of capable of understanding stellar death, we become more than just observers. We become cosmic archivists and potential stewards. This knowledge is not a passive luxury, it is a vital tool for our own long-term survival. Understanding that stars die, that solar systems are rearranged, and that galaxies evolve, forces us to look beyond the immediate horizon of our own planet. It makes the pursuit of space colonization not a mere fantasy, but a logical step in a universe where no single world is permanent. The same physics that governs a supernova could one day be harnessed here on Earth, perhaps through controlled fusion, offering a clean, stellar-scale energy source that could power civilizations for millennia. But to learn these secrets, we must protect our window to the universe. The growing plague of light pollution is slowly blinding our telescopes, washing out the faint, ancient light from distant galaxies and dying stars. Preserving dark skies is not just for amateur stargazers. It is an ethical imperative for scientific survival, ensuring that future generations can continue to read the cosmic story written in starlight. This endeavor demands global collaboration, uniting humanity under a shared goal of discovery that transcends borders. The International Space Station stands as a testament to what we can achieve when we work together in the pursuit of knowledge. Many astronomers speak of the overview effect, a profound cognitive shift in awareness reported by astronauts who see Earth from space, a fragile blue marble against the black void. Studying the cosmos instills a similar humility and wonder, reminding us that our quarrels and conflicts are vanishingly small against the grand backdrop of cosmic time. It advocates for a stewardship mindset, not only for our planet but for our role as the universe's growing consciousness. The choices we make today, from protecting our environment to fostering peace and investing in science, are the first steps in writing the next chapter of that story. Understanding the inevitable fate of our Sun, and indeed all stars, provides a powerful ethical framework. It asks us what legacy we wish to leave behind, not in decades but in eons. Will we be a fleeting flash of biological activity that flickered and died on a single world? Or will we become a species that learn to read the stars, to navigate the galaxy, and to carry the story of our cosmic origins into the far future? The answer to that question begins not out there, but right here with the choices we make today. Yet for all we have learned, the final moments of a massive star remain one of nature's most fiercely guarded secrets. The precise mechanism that triggers a supernova explosion is still not fully understood. We know the core collapses and a shockwave forms, but computer simulations show this shockwave often stalls, failing to rip the star apart. Something must reboot it. The leading theory points to neutrinos, those ghostly particles that barely interact with matter. In the unimaginable frenzy of a collapsing core, trillions of them are generated, and it is thought that a fraction of their immense energy is deposited behind the shockwave, powering it like a cosmic engine restarting. But modeling this chaotic process, where nuclear physics and gravity collide in 3 dimensions, pushes our most powerful supercomputers to their absolute limits. Each simulation brings us closer, yet the definitive answer remains just out of reach. This uncertainty extends to the bizarre matter left behind. What is the true nature of a neutron star's interior? We call it neutron degenerate matter, but that simple term hides a world of mystery. Under such insane pressures, do the neutrons themselves break down into a soup of even more fundamental particles called quarks, creating a strange quark star? Could there be exotic states of matter there, with names like superfluids and superconductors, that flow without friction and defy our earthly understanding of physics? We simply do not know. The equations of quantum chromodynamics, which govern this realm, become impossibly complex under such conditions. A neutron star is a laboratory for physics we cannot recreate, but it is a laboratory locked inside a vault 12 miles across and thousands of light years away. These gaps in our knowledge are not failures of science, but a map of its frontiers. They persist because the universe does not make it easy for us. These events are rare, with a galaxy like our Milky Way experiencing only a few supernovae per century. We cannot predict when or where the next one will occur, so we must be lucky to catch one in its earliest infancy. And even when we do, we are observing from a tremendous distance, piecing together the entire story from a single faint point of light. Our tools, while incredible, still have limits. The laws of physics themselves, our guide to the cosmos, are incomplete. General relativity describes the very large, and quantum mechanics the very small, but they refuse to speak the same language. To truly understand the heart of a neutron star or the singularity of a black hole, we need a new theory of quantum gravity, a unified framework that has eluded the greatest minds for a century. This is where the real excitement lies. Every unanswered question is an invitation, a door waiting to be opened. The fact that we can point to what we do not know and outline the path to discovering it is a testament to how far we have come. Astronomy is not a static field of facts in a textbook. It is a living, breathing, and evolving detective story. Each new observation from a telescope like James Webb, each new ripple in spacetime detected by LIGO, provides another clue. They may confirm our theories or they may shatter them, forcing us to see the universe in a completely new way. These mysteries remind us that the cosmos is still wild and unknown, and that the greatest chapters in our understanding of the stars are likely yet to be written. This cosmic detective story unites scientists from every conceivable field. Nuclear physicists work hand in hand with astronomers to model the furious fusion processes inside a supernova, using data from particle colliders to understand the reactions that forge new elements. Their complex equations describe how atomic nuclei are built and destroyed in the heart of a star's final cataclysm. Chemists then analyze the light from these explosions, reading the spectral lines to identify the specific molecules and compounds now scattering into space. This is how we know the exact ingredients being seeded into the cosmos, from the oxygen we breathe to the calcium in our bones. Even biology is deeply connected to this cycle. The radiation from a nearby supernova could be a double-edged sword for life, a sterilizing blast from one perspective, but from another, a potential trigger for accelerated mutation and evolution on a planetary scale. It forces us to ask whether such cosmic events, by altering DNA, might have played a role in the history of life on Earth. This interdisciplinary collaboration has led to stunning breakthroughs. Our understanding of how hydrogen fuses into helium in the Sun directly informed the pursuit of controlled fusion energy here on Earth, a quest to build a miniature star in a laboratory that could provide limitless clean power. The extreme states of matter inside a neutron star, where protons and electrons are crushed together, challenge our models of quantum mechanics and push nuclear physicists to devise new theories. The study of a dying star is not a solitary science. It is a grand, unified effort that demonstrates a beautiful truth: that the universe does not respect the artificial boundaries we create between disciplines. The search for cosmic answers pulls them all together, weaving a single tapestry of knowledge from the threads of physics, chemistry, and biology. That profound connection is not just abstract science, it is written into the very fabric of our being. Every single one of us is a living archive of cosmic history. The oxygen you just breathed in was forged in the heart of a massive star that died in a supernova explosion more than 5 billion years ago. The iron coursing through your veins, carrying life-giving oxygen to your cells, was hammered into existence in the final second of that same star's cataclysmic death. The calcium that strengthens your bones, the phosphorus that forms the backbone of your DNA, even the iodine essential for your thyroid function, all of these were created in stellar furnaces and scattered across the galaxy by these grand explosions. We are, as the astronomer Carl Sagan so beautifully put it, a way for the cosmos to know itself. This is not a metaphor, it is a physical fact. You are literally made of stardust. Contemplating this can trigger a shift in perspective, a feeling often called the overview effect on a personal scale. It invites a deep sense of wonder that the universe is not merely something out there, distant and separate, but that it is also right here, inside us. The same natural laws that govern the spinning of galaxies and the life cycles of stars also govern the electrical impulses in your brain as you process these very words. This realization fosters a powerful humility. Our daily concerns, while important in their moment, are set against a backdrop of almost unimaginable scale and time. The conflicts and worries that can consume us are happening on a tiny, fragile world made from ashes of the dead, orbiting a star that is itself midway through its own life story. Yet, this humility is not meant to diminish us. Instead, it creates a profound sense of interconnectedness. It reminds us that every person you meet, every living thing you see, is equally made from this ancient stellar material. We share a common cosmic ancestry that transcends all artificial boundaries. This knowledge can be a source of immense comfort and unity, a silent reminder that we are all passengers on the same pale blue dot, on a journey through space and time that began long before us and will continue long after. Astronomy, then, becomes more than a study of distant lights. It is the ultimate origin story, a narrative that tells us where we came from and how we fit into the grand scheme of existence. It has the power to transform not just what we know, but how we feel about our place in the universe, replacing a sense of isolation with one of breathtaking belonging. This grand cycle of death and rebirth is the unseen architect of every galaxy we see. A star's final act is never isolated, its influence rippling outward to sculpt the vast structures of the cosmos and govern the very pace of evolution on an unimaginable scale. Picture a galaxy not as a static collection of lights, but as a dynamic, breathing ecosystem, where the demise of its suns provides the crucial feedback that maintains its delicate balance. The most violent of these endings, the supernova, unleashes a tremendous shockwave that travels through the cold, quiet clouds of interstellar gas. This wave can compress those clouds, squeezing them just enough to trigger the gravitational collapse that births entirely new stars. In this beautiful, brutal symmetry, a star's death becomes the direct cause of new stellar birth, a cosmic chain reaction where one generation literally gives rise to the next. This sequential enrichment has gradually built up the complex chemistry we see today, directly influencing the types of planets that can form and ultimately the life that can arise. We see this history written in the stars of our own Milky Way. The oldest stars are metal-poor, formed from the pristine hydrogen and helium of the Big Bang. Their explosive death seeded the surrounding gas with the first heavy elements. Later generations, like our Sun, formed from this enriched material, containing a richer mix of elements that were gifts from the stellar generations that came before. Yet this influence is a double-edged sword. While a supernova's shockwave can trigger star formation, the incredible energy it releases can also heat vast regions of gas, making it too energetic to collapse. It can even blow gas completely out of a small galaxy, halting its ability to form new stars altogether. This is the self-regulating feedback loop that shapes a galaxy's life. It is a dance between creation and destruction, where starbirth and stardeath are locked in an eternal embrace, ensuring a galaxy does not burn through all its fuel in a single, brief burst. This legacy is not just written in the stars, but in us. Every single atom in your body, from the oxygen in your lungs to the iron in your blood, was created in the heart of a long-dead star. That carbon was forged in the gentle death of a sun-like star. That iron was hammered into existence in the final second of a supernova's cataclysm. You are, in the most direct way possible, the universe experiencing itself. You are a collection of ancient stellar remnants, assembled into a form that can look back at the night sky and wonder about its own origins. This cycle turns destruction into creation, ensuring that the end of one story is always the beginning of another. As new stars and planets coalesce from the ashes of the old, they carry forward this enriched legacy, building worlds with ever greater potential for complexity. The story of our cosmos is not one of random events, but of a profound and beautiful reciprocity, where each ending sows the seeds for a new beginning. This cosmic journey, from a nebula's silent collapse to a supernova's brilliant flash, reveals the universe's deepest rhythms. We have witnessed how a star's life is a story of constant transformation, where each ending births new beginnings. The demise of suns shows us that destruction is not an end, but a necessary phase of creation, scattering the essential elements for planets and life across the cosmos. This grand recycling of matter tells us that change is not just inevitable, it is the engine of existence itself. We are made from the ashes of these celestial giants, connected to the cosmos in the most intimate way possible. The great astronomer Carl Sagan once reflected that the beauty of a living thing is not the atoms that go into it, but the way those atoms are put together. The cosmos is also within us. We are made of star stuff. This profound truth invites us to see the night sky not as a distant spectacle, but as our own extended heritage. The next time you look up, remember that you are gazing at a past that is also your origin, and a future that holds the fate of everything. We would love to hear what this journey has sparked in you. Share your thoughts and questions in the comments below, and let's keep this cosmic curiosity alive.